Welcome, students. Today we're going to learn about reducing radical expressions with a focus on rationalizing the denominator. So let's first talk about what we mean by radical. Radical are square roots. Sometimes we can't actually square root the number nicely. We could use a calculator and get a decimal, but as you move into higher mathematics, often your teacher will want your answer in terms of a radical, a reduced radical. So if we have a square root of 2 and we have 3 of them, and we're going to subtract 8 more of those square roots of 2. We can't do the square roots of 2 without a calculator, but we can combine those because they are like terms. So we have the 3 square roots of 2 minus 8, or 3 minus 8 is negative 5 square roots of 2. Simply adding like terms or adding like radicals. Hopefully that's pretty straightforward and you remember doing that. The next thing I want to talk about is reducing a single radical that might have perfect square factors hidden in the radicand. What I mean by the radicand is the number that's underneath the square root symbol. We can take the 189 and we can factor it. So 189 is a factors of 9 times 3 times 7. If you multiply those three numbers together, you'll get 189. Likewise, I can factor the h to the fourth into two h squareds. An h squared times an h squared is the same as h to the fourth. Then I can take that single radical and I can separate it into separate individual radicals. I can square root the 9 by itself. I can square root this first h squared by itself. I can square root this h squared by itself. And then I have this 3 and 7 that I'm going to leave underneath this last square root of a 3 and a 7 because there's no other factors that pair up with that. Now we know the square root of 9 is 3. Anytime we square root something that's squared, what happens is the square root and the squared cancel, leaving just the single h. Again, so this square root of h squared is a single h. And then I combine the 3 and the 7 back together, which is the square root of 21. And then I just simplify, writing it as a 3. I have two h's that are times, so that's an h squared, 3h squared times the square root of 21. And that doesn't reduce any further. So I've reduced this square root of 189 h to the fourth to a 3h squared square root of 21. So that's reducing a single square root. Now sometimes we have distributing. And just make sure you distribute and you times that square root of 5 times each of the terms that are inside the square or inside the parentheses. So we distribute the square root of 5 times 3 is just 3 square roots of 5. We put the whole number on the front and the square root behind. And then the square root of 5 times the square root of 5 is the square root of 25. But we can square root the 25 and gives us 5. But we can't reduce the 3 square roots of 5, so we have 3 square roots of 5 plus 5. Those are not like terms, so we just leave our solution like that. But it has been distributed in and reduced. Let's do another one of those, but now we have actually the whole process of foiling. In other words, we got to make sure that when we have two sets of parentheses, that when we distribute, we multiply this first 9 by both of these terms in the second parentheses and the square root of 5 by both. So if you come down here and look, we've taken 9 times 5, which is 45, 9 times the square root of 3, which is going to be 9 square roots of 3, the square root of 5 times 5, which is this 5 square roots of 5, and the square root of 5 times the square root of 3, which is the square root of 15. Now we get to this point, we see if we can add like terms, or maybe we can reduce some of these radicals, but nothing simplifies. We can't square root the 3, we can't square root the 5. 15 is only a 3 and a 5, which neither square root, and none of them are like terms. So we just leave our answer like that. That is our solution. Now comes the hardest concept, what we mean by rationalizing the denominator. So sometimes we have square roots of fractions. What we can do first is we're going to see if the fraction underneath the radical or that radicand can reduce in and of itself, which it can. 50 over 70 reduces to 5/7. Nothing happens with the h to the sixth for a moment. Then we see if there are any perfect squares in either the numerator or the denominator. And h to the sixth has three perfect squares. It has an h squared times an h squared times an h squared. So I quickly just square rooted the h to the sixth and I got h to the third. Now be careful, notice how that h to the third is in the denominator, because it was in the denominator underneath this radical, it will be in the denominator out. So I have 1 over h to the third times the square root of 5 over 7. I left the 5 over 7. Now, what we mean by rationalizing the denominators, I don't like square roots of denominators. So what I'm going to do is I'm going to rationalize that denominator by multiplying by 1. What I mean by 1, though, is I'm going to multiply by the square root of 7 over 7. 7 divided by 7 is 1, square root of 1 is 1. So that's really just 1. So I take this expression, 1 over the h cubed times the square root of 5 over 7, and I times it by the square root of 7 over 7. Which, when I combine the two square roots, it becomes the square root of 35 over the square root of 49. I still have the 1 over h cubed on the outside. But now I can square root that 49. The square root of 49 is 7. So I come and I reduce and I pull that square root of 49 out as a single 7 times this h cubed. So I get a 7h cubed on the bottom, and then that square root of 35 is left in the top, which doesn't reduce. And that is our final solution. Let's do another quick example. I just did it in one line here. If you're given the square root of 49 over 42, first thing I do is I realize that I can square root the top by itself and the bottom by itself. I know the square root of 49 is 7, but I don't know the square root of 42. By the way, there are no factors of 42 that are perfect squares, so I didn't try to reduce it. But I am going to multiply by the square root of 42 over the square root of 42. This is 1. If I multiply by 1, I'm not changing this number, I'm just changing the way it looks. 7 times the square root of 42 is 7 times the square root of 42. But the square root of 42 times the square root of 42 is the square root of 42 squared. I have a perfect square. I can square root it now. That comes out as a single 42 underneath. So I'm left with the 7 square roots of 42 on top and a single 42 that's not being square rooted on the bottom. One last step is to see if I can reduce. And by the way, 7 goes into 42, so I have the square root of 42 over 6, because 7 goes into 42 6 times. Now we're going to try to rationalize a denominator that has 2 terms in it. Now be very, very careful here. You cannot reduce the square root of 5 over the square root of 5. That doesn't just reduce to 1. With this plus symbol, you cannot do that. So do not try to reduce top and bottom if there's plus or minus symbols between 2 terms. But what we will do is we will eliminate the square root of 5 in the denominator by multiplying both the top and bottom of the fraction by its conjugate of the denominator. Now you might ask, what do you mean by the conjugate? A conjugate is something that relates to a 2-term expression. So it is basically the exact same 2 terms, but the sign between them is changed. So for instance, if I have one number added to another number, its conjugate would be the same first number, but now minus the second number. These 2 things are conjugate. That's why I say vice versa. If you were given A minus B, its conjugate would be A plus B. Do you notice how I'm just changing the sign in between the 2 terms? So that means if our denominator of our original fraction was 8 plus the square root of 5, 8 plus the square root of 5, its conjugate would be 8 minus the square root of 5. Which means I'm going to take that original expression. Sorry, I left a little thing in there. That should just be a 5 there, and that should not be. There we go. So I take my original expression of negative square root of 5 over 8 plus the square root of 5, and I multiply it by 8 minus the square root of 5 over 8 minus the square root of 5. By the way, that's just 1, so I'm not actually going to change the value of the number. I'm just changing the way it looks. Now notice I have my single 8, I have my square root of 5, one's a plus, one's a minus. So I multiplied the top and bottom of this fraction by the conjugate of the bottom. Now let's do that. So again, I've rewritten it here, minus square root of 5 over 8 plus the square root of 5 times 8 minus the square root of 5 over 8 minus the square root of 5. And now when I do this, we got to make sure we FOIL when it comes to the denominator. But on top, the negative 5 times 8 will be a negative 8 square roots of 5. That's this times this. The negative square root of 5 times the negative square root of 5 will become a positive square root of 25. The 8 times the 8 will be 64. The 8 times the negative square root of 5 will be a negative 8 square root of 5. The square root of 5 times 8 will be a positive 8 square roots of 5. The square root of 5 times the negative square root of 5 will be a negative square root of 25. Now, if you'll notice, these 2 middle terms are exactly the same, except one's minus, one's plus. In other words, they cancel. They just get eliminated. This negative 8 square root of 5 plus 8 square roots of 5 is 0. and we're left with just the 64 minus the square root of 25. But what's the square root of 25? It's 5. What's the square root of 25? It's 5, right? Now we can actually subtract this. 64 minus 5 is 59. And on top, we're left with a negative 8 square roots of 5 plus 5 over 59, which has no square roots in the denominator, which from our original expression looks a little different, right? We have now 2 terms in the numerator, but only 1 term in the denominator, and there's no square roots. It's called rationalizing the denominator. Let's try one more or do one more example. Again, if I give you the square root of 5 over a negative square roots of 3 minus the square root of 7, what I'm going to do is multiply this fraction by the conjugate of the bottom, which means I'm going to change the sign in between these 2 terms. If it's a minus, I'm going to change it to a plus. So now I'm multiplying the top and bottom by that negative square root of 3, but not minus, but plus the square root of 7 over negative 3 plus the square root of 7. When I distribute the square root of 5 to both of these terms, 5 times 3 gives me a negative square root of 15. Positive times negative is negative. Positive times positive is a positive. Square root of 5 times square root of 7 is square root of 35. That's what I get on top. On bottom, a negative square root of 3 times a negative square root of 3 will be a positive square root of 9. A negative square root of 3 times a positive square root of 7 will be a negative square root of 21. A negative square root of 21 times a negative square root of 3 will become a positive square root of 21. A negative square root of 7 times a positive square root of 7 will become a negative square root of 49. Well, I can square root the 49, that's 7. The negative square root of 21 plus square root of 21 cancel, they're eliminated. The square root of 9 is 3, so on the bottom I get 3 minus 7. The top doesn't reduce, so I'm just leave it as a negative square root of 15 plus the square root of 35. 3 minus 7 is negative 4. Now, one thing, this answer here is correct, but a lot of times math teachers will want you to reduce. In other words, I have a couple negatives. What I've done here is I've brought the negative up, or I've multiplied top and bottom by a negative 1 to cancel the negative on bottom, changes the sign on the top. So the negative square root of 15 became positive. The positive square root of 35 became negative, and that's just because I brought this negative up and distributed it to both of those terms. So your final solution is the square root of 15 minus the square root of 35 all over 4, which has no square root in the denominator, which is quite a bit different than this. So a lot of times when you do rationalize the denominator and it has 2 terms in the denominator, you always get down to 1 term in the denominator, and you're left oftentimes with 2 terms in the numerator. Hopefully this will help you to do today's homework. If you have any questions, please get on my live office Zoom hours, and I will definitely try to help you with those.